in two parts. In the first part, I'm going to talk about fairness in algorithmic decision making in the some traditional context at the intersection of computer science and economics, which is something that I've done work more early on during my PhD and also more recently. And then in the second part of the talk, I want to try and convince you that the notions that come out of this literature from mainly from economics, these are also very easily applicable to modern algorithmic decision-making paradigms such as machine learning. Right, so this talk is going to be at a high level. I'll try to include as little math as possible, but one of the main takeaways that I want to convey through this talk is that the notions that come out of this literature are very concrete, very formally defined, and you can do some very interesting theoretical work based on these notions. All right. So as all of you know, algorithms are making decisions pretty ubiquitously in today's world in a range of different scenarios, from deciding who gets loan or who gets bail to deciding which kind of ads to serve to which users or which users to hire, or even in kind of more high stakes scenarios such as how to drive cars autonomously or whose organs should be donated to whom. And this has led to a recent surge in interest in making sure that these algorithms are making these decisions in a fair manner. And this surge has partly been fueled by some popular accounts where the algorithms were actually making decisions unfairly. And while this surge of interest has been a recent phenomenon in the machine learning and AI literatures, fairness has been studied for almost a century in this literature called social choice theory from microeconomics. So here is a paper titled The Problem of Fair Division by Hugo Steinhaus in Econometrica from 1948. And this paper studied a setting that has now become commonly known as cake cutting. Maybe some of you have heard about it. And later, this study of fairness was extended to other domains where resources are being allocated to some individuals. And in the last few decades, computer scientists also got interested in this area, which gave rise to the field of computational social choice, which basically uses algorithms for making these kind of collective decisions based on the individual preferences. And one thing that I like about this literature, and apart from the fact that I personally work on it, is that it doesn't only look at fairness as the metric for evaluating the algorithm. Fairness is but only one of the facets that it looks at. Other facets being, for example, some kind of economic efficiency of the decisions that are being made, how to actually elicit the preferences of the individuals who are being affected by these kind of collective decisions, and what kind of incentives it provides to these individuals. Maybe if the individuals might have an incentive to misreport their preferences or lie about their preferences in order to get a better decision for them. The fifth aspect that I've listed here, ethics, I've listed it, but there is a caveat, which is that ethics has received much less consideration in this literature and at least much less formal consideration than all of the other aspects. And the talk today is going to focus mainly on three of these aspects, fairness, efficiency, and incentives. And based on these kind of considerations, this literature has come up with very compelling solutions for some classic fair allocation problems. And so my collaborators and I have co-developed this not-for-profit fair division website called splitit.org. If you haven't tried it out yet, I highly encourage you to do so. So Splitit's motto is to basically take these compelling algorithms from the literature and just make them freely available to people so that they can find provably fair solutions to their everyday dilemmas. And I want to take a few minutes to just go through the 5 applications that Splitit currently offers. So the first one is called share rent. So imagine that you, a group of 5 roommates, typically students, they rent an apartment together, and there's a total, the apartment has 5 rooms, and there is a total rent charged per month. And these students, they now want to determine how do you divide the total rent of the apartment between the 5 rooms and which roommate should be assigned to which room. Okay? So what this application does is it asks each user to report what they think is a fair division of the total rent between the 5 rooms. And then based on these inputs from the different users, it computes a division of the rent between the different rooms and an assignment of each roommate to a particular distinct room, such that the following fairness property is guaranteed. Each roommate would rather have the room that they are assigned at the rent that that room is charged than the room that anybody else is assigned at the rent that that room is charged. Okay, so you won't envy anyone else for the room that they have at the rent that they are paying. And the fact that such an envy-free allocation even exists is a very non-trivial fact of computational social choice. And so this is something that we have used to really kind of get traction. This is one of the most popular applications on Splitit. So the split fare application is where a group of friends take a cab together, they drop off at different locations, and now they want to divide the total fare of the cab in a fair manner between them. The assigned credit application is where some individuals work as a group, and then the group receives some reward, and which now they want to divide between the different individuals. So they want to assess how much each individual really contributed to the group's success. And this application has been really popular with teachers because they love their students working in groups, and then they ask these students to go to Splitit and basically submit their inputs, and then Splitit finds a fair assignment of credit to the individual student, and that basically determines their grades. What I'll talk about today mostly will be based on this divide goods application, where you just have a bunch of objects or goods that you want to divide between a bunch of people. And the distribute tasks application is just the flipped version, where instead of the items that are being divided, instead of being goods, they are bads or chores that people want to try and avoid. And one thing I want to mention is that this kind of approach has been pretty popular. More than 200,000 people have used Splitit in the past 6 years to solve a range of real world problems that they have in their daily life. And in particular, if I talk about the divide goods application, as I said, you just have a bunch of items and there are a bunch of people, and you want to divide these items fairly between the people. So this basic task has a lot of everyday applications, and I've listed some applications here which are kind of real use cases based on the feedback that we have received from Splitit users. So clearly this is applied in any time where you have a collectively owned estate or some collectively owned assets to be divided between different members, such as in inheritance division or divorce settlement. But also friends have used this for splitting baseball season tickets among themselves. Teams of gamers have used this for dividing collectively obtained loot between the individual members. And some art collectors also split some collectively bought artwork using this application. So when we launched this application back in 2014, the algorithm that we had basically was the most compelling algorithm available in the literature at the moment, but it wasn't really that compelling. And the reason for that is that the kind of envy freeness guarantee that I mentioned earlier for the share rent application cannot be obtained for this particular application. So in this application, the goods that are being divided are funnily indivisible, which means you cannot take this painting and chop it up into different pieces and then allocate the different pieces to different people. You have to allocate the painting as a whole to one of the individuals. And the other thing is that you don't have the flexibility of charging payments from these individuals or agents, unlike the share rent setting. Okay, where you can actually charge a particular amount of rent to from the individuals. And that is what makes it impossible to achieve envy freeness. Imagine you just have one painting and two people want it. You have to give the painting to one of the two people and the other person would envy them for sure. So in this case, our algorithm that we had deployed back in 2014 was basically using a bunch of relaxations of this envy freeness and was trying to achieve these relaxations in as much as possible. And this wasn't really working out well in some of the instances, and we were receiving a lot of complaints from users. So here is an example complaint that we received from a group of 4 brothers who wanted to divide an inheritance of some 30 plus furniture items. And one of the brothers, he was just playing around with the website, and he was just trying it out in the demo mode. And for some of the instances that he created, the results that were given by Splitit weren't really matching up to his expectations. So he actually went ahead and created a so-called minimum working example for us. And to prevent you from having to read this text, here is his minimum working example. So he says, imagine that you have three users and you have 5 identical candies to divide between these 3 users. So what can you do? Well, if you had 6 candies, then you could give 2 candies to each user, but you have only 5 candies. So all you can do is give 2 candies to 2 of the users, and then a third user will be left with a single candy. So it's a bit unfair, but that's the fairest you can do. So to his surprise and to our surprise, actually the algorithm that was deployed on Spirit at the time gave 3 candies to the same person and the other 2 received only a single candy each. And when we dove down into what's really happening underneath, we realized that for this particular instance, the fairness property that Spirit was trying to guarantee basically said that, look, I cannot guarantee that each user will get at least 2 candies. So all I can guarantee is that each user will get at least 1 candy. And subject to that constraint, I'm going to maximize the total happiness, or what's known as the social welfare. Now, the problem with that approach is that for maximizing the social welfare or the total happiness, it doesn't really matter where these remaining 2 candies go, because whichever user gets it, it would add the same amount to the total happiness. It will contribute the same amount. And so Split just broke ties arbitrarily and gave both the remaining candies to the same person, which was obviously unfair. So this motivated us to try and find better notions of fairness that our algorithm can guarantee. And before I get into the fairness notion, let me just describe the formal setting a bit more in detail. So the input to our algorithm is basically just this valuation matrix. Okay, so as the rows, you have the different individuals who are supposed to receive these goods. And as the columns, you have the different goods. And each individual places a value on each good. And these values, we are going to assume for now that these are additive. So if this boy receives the painting and the car, then his value for that bundle would be 67 plus 150. So a bit more formally, I'm going to use capital N to denote a set of N agents, capital M to denote a set of M indivisible goods. And each agent's valuation function denoting their preferences is VI, which basically assigns a non-negative value for every possible bundle of the goods that this agent might receive. And as I said, this valuation is additive. So the value for a bundle is just the sum of the values of the individual goods in the bundle. And our goal is to compute an allocation A, which is simply a way to partition all the goods into N bundles. And then you take bundle AI and you give it to agent I, for which the agent has value VI of AI. Okay, so all that you really need to remember is that the AI that an agent I receives is a subset of the goods for which the agent has this much value. Okay, so as I said earlier, the gold standard notion of fairness in this literature is this envy freeness notion, where no individual should desire the allocation that is given to another individual more than the allocation that they are given themselves. Okay, so if you look at any pair of individuals I and J, then the value that I places on the allocation that I receives should be at least as much as the value that I places on the allocation that agent J receives. Okay? So this just says that agent I doesn't envy agent J. But of course, you have this constraint for all pairs of agents I and J. So you also have a constraint saying that J doesn't envy I. But as I said, this is impossible to guarantee when your goods are indivisible and when you cannot charge payments from agents. And so we have to use some kind of relaxations of this fairness notion. And when we were looking through the literature for a relaxation that would solve the problem from that previous instance, we found this one really compelling relaxation called envy freeness up to one good. And what this says is that, look, I cannot prevent that agents would envy other agents because these goods are indivisible. But at least if agent I is envying agent J, then that envy should be limited in some sense. Okay, so there should be at most one good, a good G in the bundle of agent J, such that if you take that good out for a moment, then agent I wouldn't have envied the remaining bundle of agent J. Okay, so even though agent I does envy agent J, this envy is kind of limited to just this one good in agent J's bundle. If you had just taken out this one good, then agent I wouldn't have envied the rest of the bundle. So it's a pretty minimal relaxation of envy freeness because you are limiting kind of the envy to only one good and you can't limit it to 0 goods. And if your goal is to just achieve this notion of fairness, then you are in luck because actually it turns out that a very simple and very intuitive allocation procedure achieves this fairness notion. And this is called the round robin procedure. And here is how the round robin procedure works. So you just line up all the items that you have in some arbitrary order. and you line up all the agents that you have in a cyclic fashion. So let's say you have 3 agents, a blue agent, an orange agent, and a green agent. So you line them up as follows, blue, orange, green, blue, orange, green, blue, orange, green, and so on. And then agents take turns in this cyclic order. And in their turn, each agent picks one item among the ones that are still available that they like the most. Okay, so the blue agent, for example, goes first. And among all the items, she picks the item that she likes the most. Then the orange agent goes next. And among the remaining items, she picks the one she likes the most, and so on. Now, I want to try and convince you that this allocation will always satisfy the envy freeness up to one good notion that I mentioned at the top of the slide. So let's see, for an example, let's see why the green agent doesn't envy the blue or the orange agents up to one good each. So to do that, I'm going to divide this allocation into phases. Okay? The first phase is going to start when the green agent picks the first item, takes the first turn. The second phase will start when the green agent takes the second item. The third phase will start when the green agent takes the third item, and so on. So if you just look at within each phase, the green agent goes first. Okay, so the green agent has the flexibility of picking any of the remaining items, and she picks this particular painting. Okay, and because of that, she must like this painting at least as much as the paintings that are picked by the blue and the orange agents after her in the same phase. So the green agent likes the painting that she picks at least as much as the paintings that other agents picks within the same phase. Okay, so if you just look at the allocation from phase 1, the green agent has no reason to envy the blue or the orange agents. She could have just picked those items if she wanted. Similarly, in phase 2, the green agent doesn't have any reason to envy the blue or the orange agents, and so on. So even across all the phases combined, the green agent has no envy for the remaining agents. So the only reason that the green agent would envy the blue or the orange agents is because they each got to pick an item before the green agent even started, before the first phase even came into play. Yeah. So if you just ignore this one item that is picked by the blue agent at the very beginning, then the green agent wouldn't envy the rest of the bundle received by the blue agent. Similarly, if you ignore this just one item received by the orange agent, then the green agent has no reason to envy the remaining bundle given to the orange agent. All right, so this is awesome because you have this very nice fairness notion. And by the way, note that this fairness notion would have solved the problem in the case of 3 people and 5 candies. Because if you give 3 candies to one person, while another person has only 1 candy, then this would violate envy freeness up to one good. Even if you hide or remove temporarily one of the candies given to the person with 3 candies, then other people would still envy the remaining 2 candies that he has left. But our goal is not only to satisfy fairness. As I said, it's also to satisfy some kind of economic efficiency. And what I'm talking about here is a very basic notion of economic efficiency called Pareto optimality, which says the following. So the formal definition might look a bit complex, but the intuitive idea is very clear. It just says that once you find an allocation A, there shouldn't be any other allocation B, a way to kind of redistribute the items among the people, such that each agent is at least as happy as before, and some agent is strictly happier than before. So if you can make somebody happier without hurting anyone else, then clearly this alternative allocation B is a strictly better allocation. In that case, your original allocation A wouldn't be Pareto optimal. Okay, so you want to find an allocation which is Pareto optimal, so you can't find a redistribution that makes people happier. And it turns out that round robin actually violates this guarantee in a very strong fashion. Sometimes round robin might come up with an allocation, and then by redistributing the goods among the people, you might be able to make every single person strictly happier than before. So that led us to this question, which is whether you can satisfy both envy freeness up to one good, so this fairness notion, and Pareto optimality, so this notion of economic efficiency at the same time. Given any evaluation matrix, does there always exist an allocation that is both fair and efficient at the same time? And the answer that we found is yes. And you can do so by choosing the allocation that maximizes the so-called NASH welfare, or the product of the values that different agents have for their own allocations. Okay, so let's see an example. Let's imagine that this is an inheritance of 3 items being divided between a brother and a sister. And these are the values that the brother has for the 3 items. And these are the values that the sister has for the 3 items, which can be different from how the brother values the 3 items. So in this case, you just want to find a way to assign each item to one of the 2 people to maximize the product of their total value. So here the assignment is going to be the following. You give the house to the brother, which gives him a value of 5. And you give the painting and the car to the sister, which gives her a value of 4 plus 5, which is 9. And then the product of 5 and 9, which is 45, I'm claiming that this is the highest possible product across all allocations in this particular case. And so there's kind of the idea of how to achieve this allocation. What this allocation really does is very simple. You just maximize the product of valuations. And I'm not going to walk you through the proof of it, but you can, we showed back in 2016 that maximizing Nash welfare would provably achieve both these fairness and efficiency notions at the same time. And one thing that I have not talked about here is that I've not talked about how do you actually computationally find this allocation. Okay, as you can imagine, maximizing the product is a very difficult objective function to optimize, especially in this discrete allocation space. Okay, so this is in fact a strongly NP hard and even APX hard problem. And so, but for this, we have an integer linear programming based formulation that works pretty efficiently for instances of up to, let's say, 20 agents and 1,000 goods. Okay? And so that's the implementation that we have deployed on the Split website. And we did this back in 2015. And since then, we haven't received any single complaint about unfairness of the algorithm, which in the absence of user study, I will take as the best indicator that the algorithm is doing its job. One thing that I want to point out is that these fairness and efficiency properties, NV freeness up to 1 good and Pareto efficiency, are not just properties that only theoreticians can understand. These are properties that are very easy to explain even to the end users, which is something that's helping us in Split a lot. And I'll talk more about this at the very end of the talk when I talk about explainability of AI solutions. Okay, before I move on, one thing I want to point out is that this literature is full of as many open questions as it's full of compelling results. So for example, here I showed that an allocation that satisfies both these fairness and efficiency guarantees always exists. And you can find it by maximizing Nash welfare, but maximizing Nash welfare is hard. So one open question is whether you can find such an allocation in polynomial time. And this is still an open question, but there was some recent progress in 2018 showing that this can actually be solved at least in pseudo polynomial time, which is something you can't even do for maximizing Nash welfare. As I said, it's strongly NP hard, which basically implies that you cannot even maximize Nash welfare in pseudo polynomial time, which is something that's slightly worse than polynomial time. Another major open direction comes from a fairness notion that we defined in the same paper where we introduced this maximum Nash welfare idea. And this is called an NV freeness up to any good fairness notion. So remember the EF1 notion, right? I said that if agent I envies agent J, then there should be some good in the bundle of J such that if you just ignore that good, then that eliminates the envy that I has for J. Now EFX basically just makes it a bit stronger. And it says that if you remove any good out of the bundle of J, that should be enough to eliminate the envy that I has for J. So even taking out the good that agent I values the least should be enough to eliminate any NV that I has for J. Okay, so the only difference is kind of the quantifier for this good in bundle of J. And for this definition, it's in fact an open question whether there always exists an allocation satisfying EFX. Okay, so even if you don't care about efficiency, if you just care about fairness, can you achieve this fairness notion? And there was some very nice progress this year. Basically, there was a paper in EC 2020, which received the Student Best Paper Award, which showed that EFX always exists when there are 3 individuals among which the goods are being divided. All right, so I talked about how this feedback from this user led us to discover this very kind of nice fairness and efficiency notion, and led us to discover this maximum Nash welfare algorithm that we have now deployed on Split, and it's being used by thousands of users. But then last year, we started thinking whether the fairness notion that our algorithm is guaranteeing, whether that's enough. And the answer that we found was that the envy freeness up to one good notion is perhaps not enough. And the reason is the following. So let's look at this example. Here, there are 4 individuals or agents. There is a circle agent who only likes the circle items. Okay, so he likes the 2 circle items at, let's say, value 1 and has 0 value for the square items. The square agent is the exact opposite. He likes the square items but doesn't like the circle items. And the remaining 2 agents, they are pretty flexible. They like all the items. And imagine that I give each flexible agent a circle and a square item, and I don't give anything to the circle or the square agents. Now, my claim is that this allocation does satisfy envy freeness up to one good. For sure, the circle agent, for example, envies this flexible agent. But if you hide this one circle good, if you remove this one circle good, then the circle agent has no value for the remaining square item that this flexible agent would have left. Okay, so the circle agent envies the flexible agent, but only up to that one circle good. Similarly, the square agent envies the flexible agent, but only up to that one square good. So even though this is fair at the individual level, up to one good, my claim is that this is not fair at the group level up to one good. Okay? So for that, let's imagine that there is a group of these 2 agents, the circle and the square agent, and a group of the 2 flexible agents. So this is called S and this is called T. And my claim is that if group S were to receive the goods that are given to group T, then what they would do is they would take these resources and they would redistribute it amongst themselves in the following fashion. The circle agent would take both the circle goods and the square agent would take both the square goods. So the group S basically comes to us and says, look, you are not giving us anything and you are giving 2 circle goods and 2 square goods to the other group T. And if we had those items, then we would each be better off by 2 units, not just 1 unit. Okay? In individual envy freeness, if the circle agent takes the resources given to the flexible agent, then he would only be better off by 1 good. But here, this group can take the resources given to another group and each member can be better off by 2 goods. So in that sense, this allocation is not fair to the groups, even up to 1 good. And when you are allocating resources, this kind of group level considerations comes up pretty often. So for example, if you are a school district dividing educational resources to teachers, you might want to be fair not only to the individual teachers, but also to teachers that belong to different geographic areas, or teachers who are teaching different subjects, or teachers who are teaching different grades, or maybe you want to be fair across teachers from different race or gender. So there are all these different groups, even sometimes overlapping groups of agents across which you want to be fair. And in some applications, you may not even know these groups in advance. And so one thing that we really wanted to do in this work is we wanted to come up with a notion of fairness that applies to all the groups at the same time without having to know the groups in advance. Certainly, the fairness guarantee would be stronger the larger your group is, but it should be a fairness guarantee that is nonetheless applied to all the groups at the same time. So without going into the math, I just want to explain at a high level what our fairness guarantee was. So this is something called group fairness. And we said that basically this mimics what we did in the earlier example. So it says that if group S, some group S, if this some group S of individuals were to take the resources that are given to some other group T of individuals and they redivide it amongst themselves, then it should not be the case that the members in S are all better off compared to what allocation they had before. Okay, so this group S cannot take group T's resources, reallocate it amongst themselves, and all be better off. Now, there is one caveat here, which is that I'm not referring to the sizes of the 2 groups. In the earlier example, this was fine because I was having a group of 2 agents look towards another group of 2 agents and decide whether they envy them or not. But certainly if you have a group of, let's say, 1 agent, and that 1 agent looks towards another group of 1,000 agents, and then this 1 agent says, if I take the resources allocated to this 1,000 agents and give it all to myself, of course I'm better off. Okay? So that shouldn't in itself be a violation of fairness. So what we do is that after this one member takes the resources given to the 1,000 agents and give it all to himself or herself, we scale the final utility that this member receives by a factor that is the size of S divided by the size of T. Okay, so we'll just basically divide her utility by 1,000 and then ask whether she is still better off compared to her previous utility. Okay. So that's at a high level this fairness notion. I want to mention that this is an exact fairness notion. There is no up to one good consideration yet. So this is in fact a strictly stronger notion than envy freeness. If you just look at groups S that are formed of singleton agents and group T's that are also singleton, then this would just basically say that a single agent shouldn't envy any other single agent. But clearly, since you can't satisfy envy freeness, you also can't satisfy group fairness. So you have to define an up to one good notion variant of this, which I won't get into the details of here for the purpose of this talk. But what we show is that if you want to achieve this group-wise fairness notion, you are in luck, because maximizing Nash welfare not only achieves individual level fairness, it actually achieves this group-wise fairness up to one good. And if you just want to achieve this group fairness up to one good without the efficiency guarantee, then you can actually just compute a so-called local optimum of this Nash welfare function, which we show you can compute in pseudo polynomial time. And there are some interesting open questions here as well. For example, can you compute this local optimum in polynomial time? In fact, if you just start with a blind local search algorithm, it just starts at an arbitrary point and just keeps on improving Nash welfare by doing some local swaps where it moves one good from one agent to another agent. Would this algorithm take polynomial number of steps or not? Okay, so we started with this individual notion of fairness that was achieved by maximizing Nash welfare, and then we showed that this individual level of fairness is not enough. We need to bump it up to group fairness, but we are in luck because even the group fairness is already achieved by maximizing Nash welfare, so we don't have to change the algorithm that is deployed on SplitIt. But then this year, we started again thinking whether the level of fairness that we now have, whether that's enough. And the answer was no. And to see why this is still not fair enough, let's go back to this again simple example with 3 agents and 4 identical candies for simplicity. By the way, if there are any questions, feel free to ask in the middle of the talk as well, especially if there are clarification questions which are kind of too late to ask all the way at the end of the talk.
There actually was one in the chat.
Oh, okay. Okay, so let me see.
I think this is from Christina.
Okay, so aren't there approaches to fair allocation that involve disposing of the excess indivisible good? The cost of envy might exceed the value of the good in some cases. Okay, so that is indeed a very interesting perspective. And in fact, there has been some recent work in fair division which consider the possibility of throwing out some of the goods. Yeah, so if you throw out some of the goods, then can you achieve envy freeness? And so achieving exact envy freeness is very difficult even when you are throwing out goods. For example, if you imagine that there are, let's say, n people, and there are only n-1 candies available, then in the worst case, you have to throw out all the candies because you can't make the agents non-envious of each other with giving them any candy whatsoever. Okay. But for some of the other notions that I described earlier, so for example, if you go back to this open question of EFX, there was a very interesting work last year which showed that if you are willing to throw out just n-1 goods, so just one fewer good than the number of agents, even though there might be billions of goods in the instance, then you can achieve EFX. Okay, so you may not be able to achieve EFX, we don't know. You may or may not be able to achieve EFX by allocating all the goods, but at least if you are willing to throw out a small number of goods, then you can achieve it. Okay, there's another question by Amir. How much of these results depend on the additivity of utility function? So all of these results depend on the additivity of the utility function. With that caveat, let me mention 2 things. So for some of the existential results, additivity is not really necessary. So for example, if you want to show that an EF1 plus PO allocation exists, for that, you don't really need additivity assumption. There are in fact more general classes of valuation functions for which this is still guaranteed to exist. But it becomes harder and harder to find those EF1 and PO allocations. You basically have to make a lot of, so it's not only computational hardness, but it's also informational hardness. So you have to ask the users a lot of different valuation queries. Okay, you have to ask the users, what is your value of this bundle? What is your value of that bundle? And one of the reasons why we chose to deploy a solution concept based on additive valuations on split it is because it is very easy for users to just put a value on each item separately. And even though this may not exactly capture their value for some of the bundles, because then you don't take into account the substitutability or the complementarities, for most of the instances and for most of the bundles within those instances, additivity works pretty well, and it minimizes the kind of the reporting burden from the side of the users. Okay, so I should also mention that in this slide and some of the other slides, I keep mentioning this polynomial time. So this is a computer science concept where you want to, where you have kind of an algorithm that makes some operations and then comes up with the final answer. And you want to bound the number of operations that the algorithm takes in as a reasonable kind of function of the size of the instance. So let's say if you have 10 agents, you don't want to solve an instance, you don't want to take a large amount of time to solve an instance with 10 agents. So there is a kind of a very nice concept in computer science to define what it means for an algorithm to run in a reasonable amount of time. All right.
California coast.
Okay, so let's come back to this this problem where I'm claiming that we are still not fair enough even after having all these individual and group level fairness guarantees. So let's look at this instance again with 3 individuals and 4 identical candies. All of the notions that I've talked about so far, they say the same thing, that in this instance, you should give 2 candies to one of the users, and the remaining 2 users would get a single candy each, and there is no way to do anything fairer than this. Except there's one question that's not answered here, which is which user would get 2 candies? Okay, and if you decide this user deterministically, then you are kind of systematically biasing the outcome of this allocation procedure towards that user. And in fact, if you go to split it right now, and if you try this instance out in a demo mode, then split it would in fact bias the outcome towards one very specific user. So for example, if you write down 3 agents, Alice, Bob, and Claire, and create 4 identical candies, then split it always seems to give 2 candies to the user who is listed first in the ordering. If the split it always breaks ties in the same way. So if you, for example, create this instance 100 times, then it's really unfair for Alice to get the candy, 2 candies each time. Now, clearly randomization is the answer here, but let me mention that this problem just wouldn't have arisen if these items were divisible, because in that case, you could just give 3 candies to the 3 people and then split the remaining 4th candy between the 3 people equally. And when you use randomization, you can kind of mimic this outcome. Okay, you can make sure that even though you can't really split a candy, you can make sure that each person gets exactly 1 full candy and a third of a candy on top of that in expectation. But you have to be careful about this. You can do this randomization in a bad manner where you just choose an agent at random and you give them all the 4 candies. In this randomization, each person does receive 1.33 candies in expectation. So this allocation is fair ex ante, so before the coins are tossed. But after the coins are tossed, ex post, the allocation is pretty unfair. Okay, because one person receives 4 candies, the other 2 people receive nothing. Yeah, so this violates EF1 and any other fairness notion that you can think of. Of course, this is a very simple instance. What you really should be doing is you should just be giving 1 candy to each user deterministically, and only to allocate the last remaining 4th candy, you should select an agent at random. And this particular randomization would not only be fair ex ante, but also fair ex post. Okay, so even after the coins are tossed, there is a certain amount of fairness in the system, which is captured, for example, by envy freeness up to 1 good. So in this simple instance, everything was very simple because the candies were identical. But when you have non-identical goods, when people have different values for the different goods, then this problem of finding a way to randomize over ex post fair allocations to achieve ex ante fairness becomes very non-trivial. So for example, you can ask, can I randomize over allocations that are envy free up to 1 good in order to achieve envy freeness in expectation? Okay, so can I make sure that no matter how the coins are tossed, agent I wouldn't envy agent J up to 1 good. But if you look at things in expectation, then the expected value that agent I has for her own allocation should be at least as much as the expected value she has for J's allocation. So before the coins are tossed, agent I shouldn't envy agent J at all. And so this is something that we did in a paper this year. We looked at a bunch of different ex ante guarantees, not only envy freeness, and a bunch of different ex post guarantees, not only envy freeness up to 1 good. But our main result was for that particular combination that I mentioned. And we showed that no matter what valuation matrix you have as input, there will always be a randomization over ex post EF1 allocations, which gives you ex ante envy freeness exact without any relaxation. And further, this kind of allocation, this kind of distribution can be computed in, again, in polynomial time. So in a very fast manner. We have some other possibility and impossibility results. So if you're interested, you can check out the paper. But again, there are also interesting open questions here. So for example, if I ask you, can you get the same ex ante envy freeness guarantee, but not by randomizing over allocations that are just EF1, but rather both EF1 and PO. So if I want to randomize over allocations that are both fair and efficient, the kind of allocations that are returned by maximizing NASH welfare, can you then achieve envy freeness in expectation? So that is an open question, and I believe one of the major open questions along this line of work. All right, before I move on to describing machine learning, I just want to say a few words about incentives. So I haven't really treated incentives so far in the talk. And in fact, all the algorithms that I described have serious incentive issues. There could be instances where these algorithms incentivize an individual to lie about their valuation function. So instead of reporting the true value for each item, the individual might report a kind of a false value for each item. And by doing that, the individual might actually receive a bundle that they like more according to their true values. So there is a notion from the game theory literature which, if you achieve this notion, then it would prevent all manipulations. At least that's the idea. And this notion is called strategy proofness. It basically says that no agent should ever be able to benefit by misreporting their valuations, regardless of what other agents are doing. So I shouldn't even care whether the other agents are submitting their true values or whether they are lying. And if they are lying, how exactly they are lying. Regardless of what they are doing, there should never be a case where by reporting a false valuation, I get a bundle that I actually like more than what I get by reporting my true valuations. And this kind of a strong incentive compatibility guarantee is easy to achieve when you have the flexibility of charging people money. For example, in the auction theory world, some of you may know about the second price auction, which is strategy proof. But when you don't have the flexibility of charging people money, then strategy proofness becomes very difficult to guarantee. Oh, so I see that there is another check. Okay, yeah. So for example, Klaus and Miyagawa in 2001 economics paper, they showed that for two agents and additive valuations, no rule, any rule that is both efficient and strategy proof would have to be some form of a serial dictatorship. So basically highly unfair. But this construction required an example where these agents put 3 different values for the different items, which led us to ask whether if you just have agents if you just have agents assigning 2 possible values to the items, so basically each agent either likes an item and has value 1 for it, or doesn't like an item and has value 0 for it, can you then do something better? And it turns out that in this case, actually maximizing NASH welfare not only retains all the previous properties I mentioned, the fairness and efficiency guarantees, but it's also strategy proof. So it doesn't give any incentive to any individuals to manipulate, and it can be computed in polynomial time. And by the way, if you are further allowed to randomize, then you can randomize over such allocations and achieve the exact group fairness in expectation. So basically you can get all the possible properties that you want by just this one algorithm. So in this binary world, you have one rule that gets you all the properties of interest. And by the way, it's not only just strategy proof, it's something called group strategy proof, which means that even groups of agents cannot simultaneously misreport in order to benefit. Okay, so that's enough about fair division. Let me now switch gears to, sorry?
A quick question.
Yeah.
But with binary evaluations, if there's ever a case where you have fewer goods than earnings, wouldn't the optimal Nash, well, like if you're doing the product thing, wouldn't you
Right.
always get 0?
Yeah, so I kind of basically did not mention a subtlety, which is that if you are in an instance, in this kind of an edge case instance where all the allocations have Nash welfare 0, which means that no matter what you do, some agent is going to go home with nothing, then you don't just maximize the product of values. You first try to find the largest set of agents to which you can give a positive value, and then you maximize the product of those agents' values. So for example, if you have 5 agents and only 4 goods to allocate, then first of all, you realize that I can only give positive utility to some 4 agents. So I fix an arbitrary set of 4 agents, and then I just maximize the product of those agents' values. And that would ensure that each of those agents gets 1 good each.
Okay.
Yeah.
And sorry, one more follow-up question on the additivity of utility that was mentioned earlier. I guess you mentioned an approach where you can query a whole bunch of different groups with various goods. But has there been any analysis on diminishing returns? For example, if I have 10 candies, I don't really care for the 11th as much as I would if it were my first.
Right. So one of the valuation functions that people have looked at quite extensively is submodular valuations. And for submodular valuations, so this is exactly the class of valuations where you have diminishing returns, where the larger the set of goods that you already have, the smaller the utility for receiving that next good. And for this class of valuations, there are some very famous open questions. So one of the most famous open questions is, does there always exist an allocation that is both EF1 and PO? So this basic guarantee, whether these two fairness and efficiency guarantees are compatible, this is known for additive valuations, but it's unknown for the submodular valuations. And as soon as you go kind of above submodular valuations, then it's known that you cannot achieve both these guarantees at the same time. Yeah, so people have done some analysis. There are some weaker guarantees that people have shown you can achieve, but nothing really compelling for the case of submodular valuations. But even in that case, even if such an allocation exists, it's known that you may need to make exponentially many queries to all these agents to find such an allocation. All right. So I have described all these preference-based fairness notions in the fair resource allocation literature. And now I want to address how you can take these fairness notions and carry them over to some machine learning tasks such as classification, clustering, or reinforcement learning. So this is some of my most recent work with my students. So fairness has been most understood in the context of classification. So let me start with classification first. The standard framework for fair classification has a list of basically a set of data points which are representing individuals, and each individual is represented by a vector X of non-sensitive attributes and some sensitive attribute A. So sensitive attributes usually represent the membership of this person to some protected class, or if the person doesn't belong to a protected class. And some of these classification tasks also have a binary ground truth. So for example, if you are trying to decide whether to give loans to individuals or not, then the binary ground truth would basically say whether this person is actually going to be able to repay the loan or not. And then you have binary classification that is desired, which is supposed to match the binary ground truth. And there are some standard fairness notions that have been proposed in the last few years in this literature, things like demographic parity or equalized odds. And I'm not going to go into the details of this because A, it's not really relevant to this talk here. And B, I think that many of you might already be familiar with that. But basically what these notions try to do is that they look at this C equal to 1 event, which is the event that the person receives a positive treatment, whether they get the loan or they get the bail, etc. And they try to equate the rate of the positive treatment between different groups of individuals, either defined just by the sensitive attribute or by a combination of the sensitive attribute and the binary ground truth. And one thing I want to mention is that these notions generalize easily to non-binary groups. So for example, if your sensitive attribute is multi-valued, okay, if you have more than 2 possible races, then these notions extend very easily, but they don't extend easily when you have non-binary outcomes. Okay, so what do I mean by that? Let's take a silly example where you are trying to decide who gets loan and who doesn't. But when you decide to give an individual a loan, there are actually 5 different types of loans that you can give to this individual. And the individuals have different valuations over all the 6 possible outcomes that they might receive, which is basically receiving either one of 5 different types of loans or not receiving a loan altogether. And in this case, it's not really clear how to take notions like demographic parity and equalized odds that define a positive treatment and a neutral treatment, and then try and equate the rate of positive treatment across different groups. You can certainly club all the 5 different types of loans into one outcome and call it giving the loan, but just equating the rate of loan being given between different groups wouldn't be fair enough, because one group might receive the kind of loans that they really want, whereas another group might receive loans at the same rate, but they might receive loans that they really don't want, or want at a very less level. And on contrast, envy-freeness is a preference-based notion that applies very naturally to this setting because it already takes into account the agent preferences, but it's quite strong. I can't really expect to ensure that no individual would envy another individual, because maybe somebody else gets a loan that I like more, or maybe they get a loan and I don't. So the idea that we explored with some students is whether you can apply envy-freeness on average across groups. Yeah, so imagine that you have a pair of groups S1, S2 across which you want to ensure fairness. And there could be many such pairs of groups across which you want to simultaneously ensure fairness. Then instead of saying that individual I shouldn't envy individual J, we just say that if you choose a random individual from group S1 and a random individual from group S2, then the individual from group S1 in expectation shouldn't envy the individual from group S2. And there are other notions of fairness from the literature that you can adapt very similarly to this problem. And one nice thing we show is that these notions don't just pop out of nothing. They actually generalize these classic notions like demographic parity, equal opportunity, equalized odds, or something that was recently proposed called equalized financial impact. And what I mean by generalize is that if you are in the binary classification setting, then you can define your groups appropriately such that these notions of group envy-freeness and group equitability reduce to whatever notions you want them to reduce to. Okay, so they basically take these notions and generalize them to the multi-class classification setting very seamlessly. And another thing that we show is that even if you want to impose these fairness notions across exponentially many pairs of groups, you only need to have polynomially many training samples. Basically, having these many training samples would be enough to ensure that the violation of these fairness notions on your training data would be similar to the violation of these fairness notions on the test data or on the underlying distribution. We also have some empirical experiments with real data sets where we measure the amount of loss that you have to face in order to impose these fairness notions. But for more details, I encourage you to check out the paper. Okay, I want to briefly describe the fair clustering problem, how you can take these kind of fairness, preference-based fairness notions and apply them to the problem of clustering. So the standard notion of clustering is that you have K, you want to place K cluster centers between N data points. But again, like in classification problem, fairness comes into play when these data points actually represent agents. Okay, and one popular application where this happens is facility location, where you want to basically cluster the individuals that are in this geographic space, and you want to find where you should build K public facilities that these individuals would access, and they want these facilities to be close to them. So formally, you are given the locations of these N agents and some possible locations for the cluster centers, and you are given a so-called distance metric D, which basically just measures the distance between these individuals and the locations of the public facilities. And the output of the clustering algorithm is a set of K cluster centers. And the cost that each agent has from this outcome is simply the distance that they have to travel to the nearest public facility. Okay, so there are K public facilities built. I'll go to my nearest facility, and the distance I have to travel is my cost. So how do we apply fairness here? It turns out that there's a notion of fairness called the core, which I haven't mentioned in the talk so far, but it's actually something that's implied by group envy-freeness. So this notion of the group fairness. So the notion of the core in this particular application boils down to something very simple and intuitive. It says that, look, there are N individuals and you are trying to place K public facilities. So whenever there is a group of at least N over K individuals, they deserve a facility to serve them. Okay, they are entitled to this facility, which means that if you have a group of individuals, S, which has at least n over k individuals, so they are entitled to a facility, and if they can find a new location for a facility Y, such that this new location is actually closer to each member in the group than the nearest facility that they have currently, so the distance that they currently have to travel, then we'll say that this is violation of the core guarantee. Okay, so any group that deserves a facility to serve them shouldn't be able to find a new location that is closer to each person than their respective nearest locations. And if you can't get this notion exactly, you might want to get an approximation of it. So for example, you might want to take the distances that this group members have to the new location that they are proposing by a factor of alpha, and then ask if this is still closer to them than the nearest distances that they have to travel. And this notion was actually explored in an ICML 2020 paper this year. And these authors showed that the exact core is not always possible to achieve, but you can achieve an approximation alpha equal to 1 plus square root 2. And with my student Evie, who is present in this call, we showed that when you are in the Euclidean space, when you're doing clustering in the Euclidean space, you can actually improve this approximation factor to 2. And we also have some computational complexity results. For example, that checking whether a perfect core clustering exists or not is NP hard. We also have some results showing that you can learn such kind of fair clustering very easily given samples. Okay, and I just want to make one note about this reinforcement learning work. So in the standard, one of the methods for reinforcement learning is this multi-armed bandit framework, where you have these k arms, and whenever you pull an arm I, you get a reward generated randomly from a distribution. And if you know all the distributions, then the answer is simple. You just want to look at the arm that has the best expected reward or the highest mean reward, and you just want to pull that arm all the time. But the main problem, the main challenge in this framework is that you don't know the distributions of the arms a priori. So you have to try and do some exploration, pull different arms. And once you kind of start learning which arms are better, you have to exploit your knowledge. So it's an exploration-exploitation trade-off. And you want to achieve some low amount of regret compared to the case where you knew the best arm and you had just pulled that all the time. So what we do is we look at a multi-agent version of this problem, where pulling an arm not only generates reward to one person, but generates different rewards to n different people. And now there is no longer a notion of what is the best arm, because each person might think of a different arm as best personally for them. Okay, so you can think of the arms as policy decisions, where if you try a policy decision, it might affect different individuals differently. So in this case, you don't want to ask what is the best policy decision. You want to ask what is the fairest policy decision. Okay? And it turns out that you can actually use the notion of Nash welfare to define what is the fairest selection of arms. Basically, you maximize the product of expected values that these agents will derive. And what we show with some students, again, including Evie, is that you can learn this fairest selection of arms with, again, this so-called vanishing expected regret in a very fast manner. Okay, so that's the end of the technical portion of the talk. I just want to end with a few important takeaways. So one takeaway is that one thing that SplitIt has shown us is that there is a very nice feedback loop between theory and practice. So not only is it the case that the strong theoretical foundations underlie the applications that are deployed on SplitIt, but also feedback from SplitIt users drive further theoretical innovations. And this happens in one of two ways. So either these users point out some problems with existing algorithms, as that group of 4 brothers pointed out, and then we derive better fairness guarantees and better algorithms, or these users sometimes point out some novel real-world domains where fairness is required. So for example, in 2015, a representative from one of the school districts in California reached out to us regarding a problem of allocating some unused physical space in public school facilities to local charter schools. So if there are some classrooms that are not really being used in these public schools, then there is a proposition 39 in California which mandates that these unused facilities must be divided fairly to the charter schools. And the law doesn't really give any formal definition of fairness, which is why this person reached out to us, and then we collaborated with them we identified some nice fairness notions, including envy freeness, and then we designed mechanisms that achieve these fairness notions for this particular problem. Another takeaway is, as I promised, I'm going to talk about explainability of AI solutions. And as I said, this envy freeness notion is nice because it's something that people can very easily understand. And without even knowing how the outcome was computed, you can just directly explain why the outcome is fair. So for example, on Split-it, we go back to each user and we provide them an explanation for why the division that is computed is fair from their own perspective. Okay, so we use only the values that they placed on the different items. And this is also useful from a privacy perspective. So they only need to know the values that they placed on the different items. And we can tell them that, look, you assigned a total of 635 points for the items that you were given, versus you only assigned 365 points to the item that this other person was given, so you don't envy them. Sometimes you might envy them, but at least if you remove this one good, then you won't envy them anymore. And these kind of explanations have really helped, in my experience, convince Split-it users to actually use this kind of allocations in practice. So Split-it is not really any kind of enforcing mechanism. Once users see the outcome, they can decide not to implement it. But I feel like these kind of explanations have really helped them come to a consensus to actually implement the outcome. And there are some important future challenges here. One is to obviously explore this kind of study to new domains. I already mentioned allocating public school facilities to charter schools. We have also done some recent work on gerrymandering or the issue of political redistricting. We are also working on this participatory budgeting framework where residents vote over how the city's public budget should be allocated. There's another important thing to do is to measure the price of fairness. So how much are you losing in other metrics by imposing fairness guarantees? And this is something we have done recently for fair division, but this is an open problem for other settings. Another thing is that these fairness notions are pretty static. So there's an important open challenge to incorporate the excess of time. And the last direction is to look at the interplay between fairness and incentives. So I mentioned this briefly in context of fair division, but this is actually more interesting in the context of machine learning. So there is a widespread belief that fair machine learning algorithms actually give some kind of an unfairly good treatment to historically disadvantaged groups to make their treatment better. And based on this widespread beliefs, there are also instances in popular media where people actually reported their sensitive attributes incorrectly. So there was some news article where a mom was arrested because she listed her white son's race as a mix of Black and Latino because she believed that the college admission process is using a fair algorithm, and basically that would give his son a leg up in the admission process. And so in this kind of context where the sensitive attributes might be self-reported, one might ask whether imposing fairness actually generates an incentive for the historically advantaged group to report themselves as historically disadvantaged. And how does that compare to the incentives that unfair algorithms gave in the first place to historically disadvantaged groups to misreport themselves as historically advantaged? And I think this is also something that Marzia, if I remember correctly, touched upon a few weeks back during the Q&A session. Wouldn't I, as a Black person, just want to report myself as white? Is there even one instance where I would not want to do that? So we have some preliminary findings here. And the key takeaway is that this widespread belief is in fact correct, but it really depends on the notion of fairness that you choose to impose. So some notions of fairness really exacerbate this problem a lot more than others. And here's a shameless plug to my other endeavor, robovote.com, which is on voting rather than resource allocation. And I was thinking about giving a talk on voting, but given the election that is happening right now, I felt that maybe it would be too much to give a talk on voting right at this moment. But if you're interested, I encourage you to check this out as well. There are very different kinds of approaches that we have used on this website. And these are the references if you want to check them out later. And thank you. I would be, of course, happy to take any questions.
Terrific. That's just wonderful. Do you want to stop sharing and then we can see more faces here? Thank you. So I'm going to first go to Marlene Colfi to ask our first question.
Yes, thank you very much, Nisarg, for this presentation. I have just like one quick question. is to know that in the example you give, like for the preference-based fair classification, it seems like we can achieve like the group fairness without achieving the individual fairness. So I was wondering if it is possible to achieve both, like in some type of.
Right. So you are exactly right that in that example, the group fairness that I mentioned is actually a weakening of individual fairness. And for most problems, so sometimes you can achieve individual fairness, but that really requires you to randomize your decisions. So for example, if you are deciding to give out loans, and if you have only a limited number of loans to give out, the only way you can make sure that nobody would envy anybody else is to randomize the allocation of loans. And so that is often not something that people prefer to do in practice. There is a big kind of challenge of convincing people to use randomization in real world. And so because of that, we looked at this average case group fairness, which is weaker than individual fairness, which is something that you can still achieve with deterministic decision making.
Okay, thank you. And the second point is like the reinforcement learning literature. Is it like possible that this could solve like the fairness question in the classification problem? I have followed like a seminar on where people try to see if the reinforcement learning could improve how people recruit other people, especially for minority and others. So it seems like using this type of algorithm tend to improve like the classification at the end, so the output that we give to people. So I was wondering if it could be a solution at the
Right.
end.
So that's a really interesting thought, because indeed you can use a reinforcement learning algorithm to learn a good way to classify. You can, for example, treat the different classifiers that you can potentially use as the arms of this multi-armed bandit framework. And then by pulling different arms and observing the kind of the fairness violation, you can learn an arm that doesn't have fairness violation. That I believe it would probably not be very efficient because there are just so many classifiers to learn from. That said, that's an interesting approach that I haven't explored. Another difference is that the fairness notion that we look at for the multi-arm bandit for the reinforcement learning work is this NASH welfare notion, whereas the fairness notion that we looked at for the fair classification was slightly different. So that could be another barrier, but in principle, what you are suggesting seems like it could be possible.
Okay, thank you.
Thank you, Marlene. Benjamin.
Thanks. I really enjoyed the talk. I think this is a really cool topic. I'm a little curious about the relationship between envy freeness and fairness, because it's they were being used kind of interchangeably, it felt like in the talk, but it feels to me like actually there'd be cases where it would be fair even with envy, right? So imagine going to the case of the paying different rents for different bedrooms in the shared apartment. Well, let's say one person was getting a rent subsidy because they were low income. Well, now I might envy the price they're paying for the room they're getting, right? But that's fine because it seems like envy freeness builds in this normative assumption that the original distribution of resources is already fair, right? And all the kind of cases you're talking about with like that people are using split it for tend to be cases where that assumption will hold, right? But there's all sorts of, that's probably more the exception than the rule, right? So is fairness more than envy freeness, and how do we expand from envy freeness to these other notions, if so?
Yeah, so that's a really great point. And let me actually break down two implicit assumptions that using envy freeness as the notion of fairness kind of has built in. And I think you kind of touched upon both these notions, but let me try and break them down separately. So one is this notion that agents are have equal entitlement, right? So agents somehow are on the same footing. They are supposed to receive the same amount, and therefore they shouldn't envy each other. Now, this assumption may not be true in some of the examples. So for example, in this case of art collectors, it is certainly imaginable that different art collectors may have put in different amount of money in the past to buy this collectively bought artwork, and then they might kind of be entitled to receive more if they have put in more money to this common pool, right? So it turns out that this is very easy to handle. If you have a weight for each user, which is the kind of the amount of entitlement that they're supposed to get, then instead of maximizing the Nash welfare, which is the product of the values, you can maximize the weighted Nash welfare, which is product of value raised to the power weight. And this is guaranteed to have weighted envy freeness up to one good, where weighted envy freeness means that once I remove that one good from your bundle, I'm not directly going to compare my value for your bundle versus my value for my bundle. I'm going to scale my value for your bundle by the ratio of our entitlements. And then I'm going to compare it to my value for my bundle. And so all of this kind of works out very naturally. And then you can extend this to the weighted setting. The other implicit assumption that envy freeness has built in is that there is no history, right? Everybody's starting from zero. And even if you have equal entitlement, it could be the case that there is some history where people have already been historically advantaged or disadvantaged. So actually, my student Evie and I have recently started working on this problem of how to do fair division when you already have a history and when you want to make sure that this history doesn't get worse and worse. Okay, so because if you just ignore history, then it could be possible that you might create additional envy up to one good for sure, but still additional envy that go in the same direction as the history. So agent I was already envying agent J from the past treatment that they two had received. And now with this new allocation, agent I again envies agent J up to one extra good. So the envy keeps on increasing. So can we try and prevent that from happening? So that's something that we are currently working on. And so yeah, very good question.
Thank you. Thank you, Benjamin. Christina.
Yes, this actually builds on that. And I would welcome any of the real philosophers in the room to tell me I'm all wet. But a notion of fairness and ethics that's always captured my imagination, I believe originated with Nell Noddings and is based in the ethics of caring and relationships. And so you talked about, it sort of relates to history, it's not quite the same, but if you told me somebody in the house was my child, that relationship fundamentally shifts how we would think about fairness. And we can think of these relationships in society that don't depend on an individual actor's history, but are sort of systemically true in terms of how we understand human relationships and sort of the demand for caring under certain circumstances.
Yeah, so that's again another great point, and that's I should have said that there are three assumptions that are built into this framework. This assumption is not only built into the definition of envy freeness, but built into the framework itself. So when I said that each agent has a valuation function, and each agent I only cares about the bundle of goods that they have received, doesn't care about what the distribution of goods is among the other agents, that was also an assumption, and that assumption is in fact not true in many of these settings, as you said. Sometimes you get some positive externality from goods that other people receive because you want to see them happier. Sometimes you have spite. You actually, regardless of whether you are getting those goods or not, you just don't want that person to receive those goods, right? And so these kind of things are something that people have also started modeling pretty recently. So there was, I think, a paper last year which looked at fair division with externalities. I believe that that's exactly the title of the paper. And this exactly looked at what happens if you, let's say, have a social network, okay, and you know that agent I gets some positive externality from some agent J receiving some utility, and you have a weight. So agent I maybe cares about agent J at a certain level, and agent I cares about agent K at a different level, right? So how do you take these externalities into account and then compute a fair division? So this, again, there are many open questions in that paper. This is really something that people have only started looking at very recently. So this kind of spite or positive externality is not something that's well explored, at least in this fair division literature.
Okay, thank you. Javad, am I pronouncing your name right?
Yeah, that's correct. Hey, it was a very great presentation. I really enjoyed it. As soon as I saw fairness in the title of presentation, I said, "Oh, I'm going to go to that presentation." But I'm kind of drifted toward the clustering method that you explained. Two questions: one, how cluster centers are being chosen, and if they're chosen randomly, how that can affect the resulting fairness. Thanks.
Right. So I didn't actually explain what our algorithm is. I just explained the guarantee that it receives, which is this kind of 2 approximation factor So I wouldn't get into the details of the algorithm, but yes, so the algorithm is deterministic. So you basically, you kind of start you growing balls around each data point. And then the first time a ball captures at least n over k data points, you put a cluster center there. So there's a whole lot of geometric things going on in the algorithm, but the algorithm is deterministic. There is no randomization there. And actually, one of the open questions is whether you can get better fairness guarantee if you allow the algorithm to randomize its choice of the cluster centers. So in expectation, if you want to achieve a better approximation of this core guarantee that I mentioned, that's unclear whether you can get a better approximation.
So would repeating the algorithm for, let's say, a number of times and then go from there would kind of somehow solve
So the algorithm is not randomized at all. Our algorithm, at least it's not randomized at all. So if you repeat it any number of times, it's going to give the exact same outcome every single time.
Yeah, I meant if you replace that with with a randomized clustering method, does it kind of affect the resulting fairness?
Right. So there are two ways you can interpret this expected distance that I have from the facility, right? You can either interpret it in the kind of frequentist manner, where you can say that if I run this algorithm many times, and then I look at the average distance that this agent has to travel to its nearest facility, then these average distances would satisfy this notion up to this better approximation factor. Or you can just think of it in one shot, but still look at these expected distances over the randomness of the algorithm. Awesome. But you are right that if you basically run the algorithm many times, then it would get a better fairness on average. Yeah. If you get a better approximation ratio.
Awesome. Thank you.
Mm-hmm.
Great. If anybody else has a question, you can use the raise hand.
Two questions in the chat that I haven't addressed. There are no other questions.
So Julian, Julian, I think maybe has had to drop off, but you can answer from the.
Okay. So maybe I can still just address the question nonetheless. Sure. So what other fairness notions besides NV freeness did you use for the facilities allocation in California? Right. So another there were two fairness notions that we looked at: NV freeness and something else called proportionality, which basically says so. In that context, it was essential to use randomization. Basically, not all the charter schools are going to get these public school facilities because there are many charter schools and very few public school resources to be allocated. So randomization was kind of key there. And so another thing that we looked at is that and the charter school had kind of a dichotomous utilities. So they either get enough facilities inside a public school campus and they can just relocate to that public school's campus, and then they can save on rent that they were paying at their own kind of currently rented facilities, or they don't get enough facilities from any single public school campus and then they have no value for it, right? So it was kind of a 1 or 0 kind of situation. And then the notion that we looked at for fairness, this is called proportionality, basically just guaranteed that each of the n charter schools should have at least 1/n probability of getting enough space in a public school facility. So basically, you should get at least at least as much value as a random dictatorship mechanism, right? So if you were chosen dictator at random with probability 1 over n, then you could have just gotten utility 1. So you should at least get that much utility. Okay.
Can I? Yeah. So I want to ask a question, but Francois, but I think the question was answered. But so I have 2 questions for you. And I'm really delighted to see you thinking about, both building this website, split it, and so on, and really paying attention to how does this help us with real world problems. And so I have two questions there. One is about what's your sense of the domain of these of where these kinds of allocation mechanisms can be valuable, like as a share of all the fairness questions that we face in the world. Because sometimes I feel like, well, they have some fairly restricted domain, we're dividing up an inheritance, but your examples there gave me a sense of maybe it's broader than that. And relatedly, I think the second question, how much of our sense of fairness, this is a conversation we've been having among people at the Institute lately, you know, how much of our assessment of fairness is based on the process as opposed to the allocation? So they start to merge for some of what, when you start to put in randomization, and to what extent are people saying, I evaluate this as a fair process, and therefore, whatever the outcome, and you're proving characteristics that a process will produce, but you're still applying your fairness definitions to the actual allocation rather than the process. So
Right.
anyway, I asked this, so both bundled together. I think they're related, but maybe they're not.
Yeah, they're definitely related. So let me answer the first question. So if you want to look at the kind of the broader set of possible questions where these kind of fairness notions can be applied, the broadest question that you can think of is that there is a decision to be made. There are a bunch of different possible outcomes for the decision. And maybe it could be one decision or a number of different decisions that you have to make, maybe over time. But at the end of the day, there are multiple individuals which are affected by these decisions. And each individual has preferences over what decisions are better for them. And then you want to find a fair decision to make a fair collective decision, which affects all these different agents at the same time. And so these are the kind of cases where these fairness notions can be applied. So for example, when you are looking at fair clustering, it's not really that I'm personally allocated something. There's just a public outcome, these locations of the K public facilities, and these public outcome affects all the N individuals at the same time. And then you can ask whether this satisfies a particular fairness notion or not. For the second problem, so this distinction, I know about kind of the huge literature on the distinction between the fairness of process versus the fairness of outcome in kind of the philosophy literature, in governance literature. But in computer science, at least from the computer science side, this issue hasn't received much attention because the way computer scientists tend to look at a process as just a function that takes an input and produces an output. Now, what the function does in between is not really relevant in the sense that all the processes that take the same input and produce the same output are basically the same function. And so that's the kind of view that computer scientists tend to take, which is why only outcome-based fairness notions have received more attention in computer science, not the process-based fairness notions. But that said, I'm certainly kind of open to exploring how to distinguish between different processes, which might nonetheless lead to the same outcome, and how to define kind of a fairness notion based on the process. So I know that this is not really a satisfactory answer, but this is still kind of nonetheless.
Well, we've got lots to talk about. So we've got it's ongoing conversation. Alex, do you want to ask your question?
Sure. It was just very related to the question that you had asked, but I was obviously with the election going on, there's a lot where people have very differing views of what's fair, and where the number of agents, I know you were discussing like multi-agent situations, but where the number of agents is enormous. Do you think your like a split it or something would be effective when considering things like at that larger scale?
Right. So there are two questions here kind of. One is whether computationally something like SplitIt can handle a large number of people, and something as large as the size of a country, certainly not, because these are NP-hard problems that SplitIt is solving in real time. But the other question is whether these fairness notions themselves are applicable at such a large scale, and whether they make sense and are strong enough at such a large scale. So notions like envy freeness for sure, but then they would be very hard to guarantee at such a large scale. That's why notions like core, which look at what a group is entitled to and whether this group is receiving treatment that is comparable to their entitlement, these kind of notions are very much applicable. So for example, I mentioned this ongoing research that we have on participatory budgeting, which is something that actually Toronto also experimented. They did a pilot from 2015 to 2017, I believe, a 3-year pilot. But they haven't really continued ever since. But this is something that Paris and New York and San Francisco, these kind of big cities, are really driving this participatory budgeting. Paris is, for example, allowing residents to vote over how more than $100 million of budget is allocated each year. So people in Paris basically vote over how this money will be spent on repairing roads or building some parks in the neighborhood, etc. And in these kind of settings, this notion of the core is very nicely applicable. In fact, there's a major open question in participatory budgeting literature whether exact core fairness can be achieved or not. And basically this notion says that any community, so it doesn't, you don't even have to look at predefined groups of people. Any group of people, any group of residents in the city, they deserve a proportion of the budget spent on their needs, right? So if there is $100 million that the city has made available, and if you look at any, let's say a third of the population, then they deserve 33 million basically spent on their preferences. So if they can find a better use of those $33 million, if they can send that, they can say that if we had access to this $33 million, then we would have funded projects B, C, and E. And that would have given each of our members a better utility than what you are doing with this money. Then we say that the core fairness is violated. So basically no group of individuals, no matter how you kind of select this group of individuals, doesn't have to be based on area or based on race. Any group of individuals shouldn't be able to find a better use of their entitled share of the public budget than what the city has done. So that's kind of a notion, and there is a major open question whether that's achievable or not. But nonetheless, it seems achievable, at least in kind of millions and millions of simulations. And that's a notion that people are kind of really falling behind in this literature. So there are certainly notions that are applicable at that scale. Now, in particular to the problem of voting, so when you are making a complex decision, so either something like this participatory budgeting, right, where you are choosing that, okay, I'm going to fund projects A, E, and D. So if you are making that kind of a complex decision, then fairness comes into play, because you can make sure that if there are, let's say, 100 residents who like projects A and B, 100 residents who like projects C and D, and if you only can fund 2 projects, you can make sure that you fund project A, which is liked by these 100 residents, and project C, which is liked by those 100 residents, so that each person gets something out of it. In a more or less binary decision, if you are making a more or less binary decision, then fairness definitions really break down. Because, I mean, like in the current election going on, right? No matter who wins, almost half of the population is going to be really upset. So one thing that my research on voting has focused on is how to not think of the problem as a 0 or 1 problem. Most often, it's not that you are making only one decision at a given time. You are actually making several different decisions at the same time, right? You are deciding some ballot races, some Senate races here, presidential election here, some other races down ballot. So if you are making all these decisions at the same time, now suddenly fairness comes into play, because you can make sure that if some decisions are made in a way that makes one part of the population happy, then other decisions are made in a way that makes other part of the population happy. And this can not only be part of the election, this can be applied also on the final decisions that these elected representatives make, right? So for example, if you are selecting economic policy versus immigration policy, you can make sure that the policies are not selected in a way that completely kind of makes one subgroup happy while completely disregarding the preferences of another subgroup. So hopefully that also partially answers your question.
Well, thanks, Nisarg. That's a place to stop as we all go back and refresh our browser screens on results from that other election. Terrific talk. Thank you so much, everybody. Thank you for being here. Just a reminder, here we go. A reminder that we are not having a seminar next week. As it's reading week, we will be back on November 18th with Anita McGann. Speaking on, if I recall, let's see, mobility and proximity in Canada during the COVID-19 pandemic. So we will look forward to seeing you all then. Take care. Thanks a lot, Nisarg. Bye.
Thanks everyone for tuning in.